All right, so first thing, we had an exam scheduled for Tuesday that we had to postpone. So it's going to be next class, Tuesday, instead. So exam 1 is Tuesday, 1, 2, 3, 4, 5. Yeah. And the topics. Now, remember, the exams are all problem solving. They're not like the quizzes where you're just answering questions about the lecture or anything. There won't be anything like that. It's just answering, doing problems. And the problems are going to be similar to the ones that are on the assignments. And so the topics that you're responsible for are everything up through particle free body diagrams. So there won't be any doing particle statics. You might ask yourself how I plan to write an hour and 20-minute exam based on all the stuff, only including particle free body diagrams. And I don't know, it's going to be a challenge, but there's going to be a lot of vector questions and a few free body diagrams. But anyways, so it lets you sort of ease into getting ready for this. You don't have too much stuff you have to focus on. And I will have office hour. I have an office hour today. And then I have 2 office hours on Monday. Those are all in the tutoring center. So, if you want help with any of this stuff, I'll be available then. Does anybody have any questions related to homework questions or anything about the exam? Yes. Sure. Yeah. So that is not related to the particle free body diagrams because no moments occur on particles. But I am going to talk a lot more about moments and rigid bodies and stuff today. So let me just, I think that'll sort of come up as I'm going today. But I will say there are 2 ways that moments can come up. Moments can come up by a single force applying a moment. And in that case, you just draw the force. Or it can come up as a couple. And I'll define what a couple is, and we'll talk about that. But when you're dealing with couples, you can think of those as just pure moments. And in that case, you don't draw the forces themselves, you draw the moments. And you can represent those like this if you're dealing with a 2-dimensional problem, 800 Newton meters. Or in 3D, you can represent it as components of a vector. And the way you know that you're dealing with a couple and not a force is that you put double arrows on the components. And so you would write this as like 800 Newton meters, negative 400 Newton meters. Or you could, at negative 400, you could also do it like this. Some people like to do it like this. Just draw this in the opposite direction and then call it positive 400. So those 2 things mean the same thing. Any other homework questions? Okay. So back to moments. So let's go back to this idea of what a moment is, this intuitive idea. And I want to say something about um, intuitively understanding the direction of a moment. Okay, so say you have this wrench and you're applying a force that way. And um, this is the about point, the center of the, the place where it's going to start moving. And the row vector is this. So if there were no other loads or moments applied here, the force applied by F would make this thing rotate that way, right? Counterclockwise. Anybody have trouble visualizing that? And so moment is a vector. We know that it's a vector because it's defined by a cross product. The output of cross products are vectors. And so intuitively, what's the direction of this moment vector? Well, the way to think about that is think about the direction of rotation that would occur if there was nothing preventing rotation. So if all you had was this moment, this wrench would rotate that way, right? And now think about the right-hand rule, where your fingers are rotating in the direction that that moment is causing a rotation. Okay. So in this case, this is causing a counterclockwise rotation. And so your fingers rotate counterclockwise, then your thumb is pointing in the direction of the moment. Okay. So your thumb is in the direction of the axis of rotation following the right-hand rule. It's easier to visualize in 2D problems, but it's always true. And so let's see. So if you that's your clawed talons. Okay, this is making this picture way worse. But so if your fingers rotate in the direction of the rotation that would occur, your thumb is pointing out. So this force applies a moment in the direction straight out of the page. Any questions about that? And there are a couple of things that I want you to keep in mind about moments. So notice. The first one is in using the moment balance equation. That's what I'm going to call rotational Newton's second law, because I like abbreviations. You need to keep the same about point for every force, okay? You have to use the same about point for every force in the equation, to calculate every moment. So once you choose an about point, you can choose any about point you want in statics, not in dynamics. But once you choose the about point, you have to keep that same one. Otherwise, you could move the about point to the place where one force is applied. It would produce zero moment. Then you could move it to the place where the next force is applied. That's zero moment, and you never have any moments. And we know that's not true. Okay. What? Yes, that's right. So yeah, use the same about point, and this is the A that I have drawn in there. In 2D problems, Newton's second law gives two equations. The moment equation, Rn2L, gives one equation. And the reason rotational Newton's second law only gives one equation is because the only non-zero component in 2D problems of a moment is the z component. And so altogether, you get three equations. So you can solve for three variables. In 3D problems, Newton's second law, you have three components of the forces, so that gives three equations. The moment equation, now you have three components of your moment vectors in general, so that gives three more equations. And so altogether you get six equations. And so you can solve for six variables. Okay, I'm going to do a couple example problems. Anybody have any questions about anything I said here first? All right, well, I'm going to start with a 2D example problem. So let's say we have sort of a Ford, and let's say that it has a length of 2 meters and a width of half a meter. And let's say that we have a force acting this way of 20,000 newtons. And let's say there's another force acting here of 10,000 newtons. And let's put the about point here. What's the sum of moments about A? Well, I'm going to write out this little 3-column table that I mentioned before. So we're going to, for each one of those two forces, we're going to calculate the row vector and the force vector, and we're going to rho cross F is equal to M, so we'll calculate that moment vector. And for now, I'm going to do it all in 3 dimensions. I'll probably do that in all my example problems for a little while, and then eventually I'll we'll see the pattern and sort of go to a shorthand. But okay, so for the first force, let's call the 20,000 Newton force the first one. So the first row is all going to be related to that 20,000 Newton force. The place where this 20,000 Newton force is applied is here. So row vector for this first force always goes from the about point to where the force is applied. So that's the first row vector. Can anyone tell me what the components are of that vector? That's right. Yep. 2 in the positive x direction, 0 in the y direction. And so 2, 0, and like I said, I'm going to, for now, write these as three-dimensional vectors. So we'll just write 0 for the z component. And what are the components of the 20,000 Newton force? Yep, 0, positive 20,000, 0. And the cross product of 2, 0, 0, 0, 20,000, 0 is just 0, 0, 40,000. This is the blue one. So 40,000 means 0, 0, 40,000 means magnitude of 40,000 coming out of the page if we're using a coordinate system like this, is what we had to be doing to come up with these components. So does it make sense to you that if this about point was the point of rotation, this force would cause a rotation that would correspond to your thumb going out of the page? Okay, think about that intuitively. That rotation, if you applied that force up like this, it would make it rotate counterclockwise. Okay, so rotate your fingers counterclockwise, your thumb comes out, and out has to be the direction of the z-axis. Okay, so the intuitive sense of what the moment is works out with the vector map. Okay, and now the second force, the 10,000 Newton force, our row vector goes from A to where that force is applied. So what are the components of that row vector? Two, negative, half, 0. That's right. So positive 2 in the x direction, and then down 0.5, so negative y direction. So 2, negative 0.5, 0. And then what are the components of the force vector? Yep, 10,000, 0, 0. And now the cross product is 0, 0, 5,000. Now, again, let's think about this intuitively. Does it make sense that, so to make sense out of this, I think, imagine sort of causing this force by tapping it with a hammer rather than pulling on it, because imagine pulling on it, you can sort of misunderstand how this works. We're just talking about right at this instant. But if you had a little protrusion here that you could tap this way with a hammer, which way would it make this body rotate? Counterclockwise again. Okay, it's like, just like if you tapped it on this side, it would make it rotate that way. And so your fingers go counterclockwise, your thumb goes out, so that needs to be a positive z component, and that's what we got. So now the sum of the moments is 0, 0, 40,000 plus 0, 0, 5,000, and you get 0, 0, 45,000. And it's in Newton meters. Equivalently, you could write this, and this is what we're going to do eventually just to save keystrokes, whatever, but rho F moment. If we're thinking about this as a 2D problem, we can think about the row vectors as 2, 0, and 2, negative 0.5. We can think about the forces as 0, positive 20,000, and 10,000, 0. And then since we know we're only going to have non-zero z components, we can think of the moments here as 40,000 and 5,000. But you know, mathematically, you can think of it this way, and then you don't have all the zero components in your equation. But you should keep in mind that a moment is always a vector, and keep in mind what it means intuitively. Okay, let's do a 3D problem. So this time, let's say there's a plate. And let's say it's connected to the wall by a hinge. We'll talk about dealing with hinges pretty soon. But let's say right at the center, there's a cable connected to this plate, and that cable connects to the wall above it. Okay. And we'll use a coordinate system like this. I'll call this X, this Y, and this Z. And let's say that this is the about point. Now, if we know that the cable force, the cable tension, is 10,000 newtons, what's the moment applied by the cable about A? What's the moment the cable applies about that point A? Okay, well, I'm going to write out rho, force, moment. This time we don't expect any, in general, we don't expect any zero components. I mean, sometimes you get them, but they can all be non-zero. We're only dealing with the one force, so we're only going to have one row in this table. So the row vector goes all the way from that point A to the point where the force is applied. Where does that cable force, where does that cable apply a force to the plate? Right, that's right. So This is the row vector. Oh, and can you do this without any dimensions? No. That was a test of my ability to remember to write stuff. Okay, so let's say that it's 2 meters long. Let's pretend I said this at the beginning. 2 meters long. Oh, I guess it's supposed to be a square. It doesn't really look like it, but 2 meters wide. Okay. And that cable's supposed to be right in the middle. Okay, so what are the components of the row vector? So we know we're trying to come up with the components, that orange vector. And so just think of taking a trip one by one parallel to these axes. How do you get from A to the center? So you have to go 1 meter along the edge. It doesn't matter what order you go, but 1 meter along the edge in the negative x direction. Okay. So the first component is -1. And now you're here, you're on the side, and now you have to go in the z direction 1 meter. The positive z direction. And then you're there. You don't have to go up and down at all. So the y component is 0. Any questions about that? Getting comfortable doing this kind of stuff is going to be like how you do in this class is going to hinge on that sort of to a surprising degree, you know. So if that stuff, if you're not comfortable with that, then we should talk about it more. You should work on that. That's going to be a big thing. Okay, the force vector. Oh boy, the force vector is going to be a pain. So how are we going to calculate the force vector? Oh, and damn it, let's also pretend that I gave you this dimension. This is 1 meter. I have to give you all that stuff or you can't do this. Okay. How are we going to come up with the force vector? We know the magnitude is 10,000 newtons, but that's not a vector. What do we know about the direction of that force? Yeah, so we know that a cable applies a force parallel to the cable away from the body. So we know it goes in the direction from here to here. Okay. And so let's get a unit vector that goes in that direction. And then we'll multiply that unit vector by 10,000. And then that'll be our force vector. Any questions about that? Okay, so the first thing we want to do is come up with just, it's not going to be a unit vector, but we want to come up with a vector that goes from where I drew the origin, where the force is applied, to the connection with the wall. So we have to come up with the components of a vector going from here to here. To do that, you would go 1 meter in the negative x direction, 1 meter in the positive y direction, and then 1 meter in the positive z direction. So this vector is -1, 1, 1. Any questions about that? That's not a unit vector, though. If you calculate the magnitude, it's not equal to 1. So now we have to turn that into a unit vector. So the magnitude of this vector is square root of 3. And then finally, divide each component by that magnitude. And the unit vector is, it's -1 over root 3, +1 over root 3, +1 over root 3. In decimals, that comes out to -0.577 And then the other ones are the same but positive. Oh, since we're going to multiply it by 10,000, I'm going to put in one more significant figure. And now the force vector is just 10,000 times that. So we have negative 5773, positive 5773, positive 5773. And now I can put that in the column for the force. So negative 5773, 5773, 5773. Any questions about that? And now the moment, I mean, I would recommend you just plug it into your calculator and have it do it, but you get negative 5773, 0, negative 5773, and that's the moment. And what that says is if this object was free to rotate about that point A, if that was like a ball and socket joint, and you applied a force in the direction of that cable with a magnitude of 10,000, the axis of rotation would have one component in the negative x direction, one component in the negative z direction, and no component in the y direction. Again, it tells you the axis of rotation according to the right-hand rule. Any questions about that problem? Okay. So these are the moments of a force. Now we're going to talk about the moment of a couple. And I'm going to just call it a couple. People usually just call it a couple. But there's something special about a case where you have two forces that are equal in magnitude and opposite in direction, acting at some distance apart from each other. So a moment couple is two equal and opposite forces acting at a distance. An example of a couple is like a screw. Well, really, have you ever seen, sometimes you have bolts and stuff that instead of having a slot like this for a screwdriver, they have two holes for a spanner, and you put a thing in each one. And it works the same as a screwdriver, but to turn this thing, one piece of the spanner applies a force that way, the other one applies a force that way. That's how a screwdriver works too. It's just that then you have infinitely many forces doing that. You can still think of that as a force that way and a force that way. And that's how you turn a screw. That's also when So this is like a quarterback. Okay. So when a quarterback's getting ready to throw and a 300-pound guy hits him like this, and a 300-pound guy hits him like this, um, he rotates very quickly down onto his back. And it's the same idea as the screwdriver. You have two equal and opposite forces acting in at a distance, and it causes a rotation. And you can think of couples. You can think of a couple as a pure moment. And so when we encounter a couple in a problem and we're writing out this list of row, force, moment vector, you can forget about these. These aren't going to matter for anything. The reason the force itself, like, why isn't it going to matter in a problem what this force is? Aren't we going to have to include these forces in Newton's second law? They're equal and opposite, so they cancel each other always. That's how a couple works. So that's why we don't care about the force. If we don't care about the force, we don't care about the row vector. The only thing we care about is the moment. I'll write it as m sub 0 or something. And so even though what a couple is two equal and opposite forces, we're going to always represent it mathematically as just a moment that's added on. Okay. And there's something surprising and really different about the way a moment works that's provided by a couple. So here's the big deal about couples. The moment they produce is the same no matter what the about point is. Okay, so let's look at a case where we just have a single force applying a moment. So in this problem that we just did, we chose an about point over here, right? And based on that, we did this calculation and we came up with a moment of negative 5773, 0, negative 5773. What if we move the about point? Are we going to get the same answer or a different answer? It's going to be different, and the easiest way to see that is what if we moved our about point to the spot where the force was applied? Well, then the row vector is 0 and you get no moment. That's another case of like if you have a bolt that you're trying to turn and you try to turn it by applying a force straight down over the bolt, it'll never turn because it doesn't produce a moment. Okay, so in general, the about point determines, has an effect on what the moment is. But let's see how it works with a couple. Okay, so I'm going to give, it's short, but I'm going to give a little proof of this. So let's say we have a body here, and I'm going to call that point P1. And I'm going to call this point P2. And we're going to apply equal and opposite forces. So I'll call that one force F. And that one, they're equal and opposite, so that has to be the force negative F. And then we'll just choose some arbitrary about point. So I'll call this the about point A. Okay. And what's going to happen in this proof is we're going to go through the calculation of the moment produced by this couple. And that A that's going to start out in there when we go through all the algebra is going to disappear. And what it's going to say is it doesn't matter where A is, we get the same answer. Okay? So we'll call this row 1. And we'll call this row 2. Let me get this in words. So what we're going to do is calculate the sum of the moments produced by this couple. And we're going to show that it doesn't depend on A. Anybody want to ask any clarifying questions or anything to make sense out of what I'm doing here? Okay, so we're going to think of these as two independent forces. The moment produced by this force F is going to be rho 1 cross F, right? The moment produced by this force is going to be rho 2 cross negative F. Everybody with me on that? Then we're just going to add those together and stuff's going to cancel out. So the sum of the moments about A is rho 1 cross F plus rho 2 crossed with negative F. Now we can clarify what rho 1 and rho 2 are. How would you represent this vector rho 1 in terms of P1 and A? So I'm going to replace rho 1 with, if we know the coordinates of P1 and A, how do you represent a vector that goes from A to P1? Yep, good. So P1 minus A crossed with F. And how do you represent rho 2? Yep, quantity P2 minus A crossed with negative F. Now the cross product, you can distribute this multiplication, this cross product. So that's equal to P1 cross F minus A cross F. And the second one is P2 crossed with negative F minus A crossed with negative F. And now you can pull the negatives on those last two expressions out to the front. So you get P1 cross F minus A cross F minus P2 cross F plus A cross F. And the only two terms that have a dependence on A, you have a negative one there and a positive one there, so those cancel. And what you get is, now we can regroup these if you want to sort of simplify this, and you get the quantity P1 minus P2 crossed with F. So no matter what you choose as your about point, the about point, the moment produced by that couple is the same. Okay. And so that's why we're never going to, like in free body diagrams, represent a couple as two equal and opposite forces. We're going to represent it as just in 2D as a little like semicircle arrow. In 3D, we're going to represent it as components, and it's just going to have a value or a variable associated with it, you know. So let me draw the example we're going to do now. So let's say that we have a disk in 2D, and we're going to use a coordinate system like this. We're going to use an about point like, well, let's leave that off for now. There's going to be a force right over here of, we know the direction, but we don't know the magnitude. So let's say that this force is F2. And on the other side, there's a unknown force vector. We'll call it F1. And then down at the bottom, there's a couple. And we're going to represent that like this, with a value of negative 450 Newton meters. We know that we're given this angle, let's say that's 30 degrees. And we want to know what are that vector F1 and that scalar F2. Okay, so instead of drawing that couple at the bottom as two equal and opposite forces, we forget about the forces. We just treat it as a pure moment that's either counterclockwise negative 450, or you could also, I could have drawn it as a clockwise thing and called that positive 450. But isn't there a problem with, we haven't chosen an about point yet? Isn't that the moment produced by that couple going to depend on where the about point is? No, that's the idea of that proof we just went through. No matter where we put the about point, that's the moment produced by that couple. No other forces work that way, but equal and opposite forces do. Okay. Who's with me? Okay, so to do the problem, let's choose the about point here. And I'm going to write out rho, force, moment. And I need some dimensions. The radius of this disk. So let's say the radius is 1 meter. Okay, so let's start with this force F1. So the first row is going to represent F1. What's the row vector for that force? It goes from A to where the force is applied. So it's going to go one radius of the circle in the negative x direction, and then one radius of the circle in the negative y direction. So negative one, and then 0 for z. Any questions about that? How are we going to represent that force vector? Well, we don't know anything about it. It's just an x and a y component. So I'm going to write that as just f1x, f1y, 0. And the cross product of those two vectors is negative f1y plus f1x. And then I sort of glossed over the components. But it would be 0 for an x component, 0 for a y component, and then negative f1y plus f1x for a z component. Any questions about that? Now we'll go down to the second force. And this is F2. Okay, what's the row vector for F2? One, negative 1, 0, exactly. 1, negative 1, 0. Because you have to go, so you start out at the about point, you go one radius in the positive x direction, one radius in the negative y direction, and then you're there. And how are we going to represent that force? Well, we know the direction. So if you put the tail of that vector at the origin, we know that this angle is 30 degrees. And so that unit vector is just cosine and sine of 150 degrees. And then that's multiplied by F2. Right. And so you can just write that as negative 0.866 F2, positive 0.5 F2, and then 0 for z. And the cross product is 0 for x, 0 for y, like always in 2D problems. And then 0.5 F2 minus 0.866 F2 Since that's all F2s, we can write that. So that's 0, 0. Yes. And so that's negative 0.366 F2. And the last thing we have to deal with is the couple. So I'll write that as the negative 450. For a couple, we don't care about either of these things. We only care that it, we only care what the moment is it produces. We know that it's in the z direction with a value, a component of negative 450. So 0, 0, negative 450. All right, so now that table's filled out. And now we're just going to get what we can out of Newton's second law, and get what we can out of the rotational Newton's second law. Well, how many equations are we going to get? How many useful equations in a 2D statics problem? 3. 2 useful equations from Newton's second law, 1 useful equation for the moment equation. And we have 3 variables, f1x, f1y, and f2. So we should be able to solve for it if none of those equations are multiples of each other. So Newton's second law. I'm only going to keep the x and y components because the z components are 0. So we have f1x, f1y, plus negative 0.866 f2, positive 0.5 f2. And it's static, so that's equal to 0, no acceleration. So we have a first equation that says f1x minus 0.866 f2 is equal to 0. The second equation that says f1y plus 0.5 f2 is equal to 0. And then the moment equation, we only care about the z components here. So we have negative f1y plus f1x minus 0.366 f2 minus 450 is equal to 0. Because in statics, you add up all the moments, they have to equal to 0. And that gives us a third equation that says negative f, let me put them in the same order that I have up above. So let's say positive f1x minus f1y minus 0.366 f2 is equal to 450. Okay, so now we have a system of 3 equations for 3 variables. This is a small system, so you could do this substitution without too much trouble, but if you want to do it in your calculator, it would have 3 rows, 1 for each equation. 4 columns. So these rows are going to be equation 1, equation 2, equation 3. The order that I put them in, I have my F1 x's as the first column, F1 y as my second column, F2 as my third, and then the constants. Okay, so what values go in the elements of this matrix? From equation 1, what do I put in the F1x box? 1. What do I put in the F1y box? 0, yep. F2, yep, negative 0.866, and then no constant. For equation 2, we have 0 for F1x. For F1y, we have 1. For F2, we have 0.5, and then 0 again for the constant. And then for 3, F1x, 1, F1y, negative 1, F2, negative 0.366, and the constant 450. And then use reduced row echelon form, and you get that this force F has to be equal to 389.7 for the x component and negative 225 for the y component, newtons. And F2 has to be F2 has to be, yeah, 450 newtons. Okay, so that's our first rigid body statics problem. We went into this problem knowing some stuff, just not knowing. So we knew something about the form of these forces that are being applied. We didn't know anything about this force, but we knew the direction of this one. Okay. How we know that is sort of the next big topic we're going to get into, but for now, we're just saying this is what we're given. And we're trying to figure out what those forces have to be if we know that this thing stays at rest. Okay, so this thing's just sitting there on the table or whatever. We know this is the form of the forces, and we were able to calculate what those forces had to be. Any questions about that problem? Okay, that's almost a full two-dimensional statics. There's just one more step that we need. And that is, we're usually not given the forms of the applied loads themselves. Instead, we're usually given what types of joints connect this body to the surroundings. So what types of joints connect the body to its surroundings? Um, okay, so let me draw this problem again the way the way we would see it in like a full statics problem. So the problem above might appear something like this. So over here is a wall, and the body is connected to the wall by a pin joint like that, sort of like a hinge. And then over on the other side, so let's say there's another wall like this, and over on this side, there's another pin that can slide freely in this slot. And then down here, say that we're given the couple again, like that might be a couple that's coming from the shaft of like a engine, a motor or something, okay? And so the next thing that we have to get into is how do we go from a picture like this, where we know the type of joint here and the type of joint here, to re-representing those in terms only of the loads that they apply. And so the next thing we're going to talk about is a step going from this to the form of the problem that we were given, that we solved. Okay. Anybody have any questions about that? So next time, on Tuesday we have the test, and so this will be on Thursday of next week. So the next topic is going to be what types of loads are applied by each type of joint. Okay. All right. Well, it's been nice seeing you guys again. Time for another weekend. Enjoy your time off. See you Tuesday. So like I said, I have office hours at like basically now at 2 o'clock in the tutoring center, and I have office hours from 2 to 4 in the tutoring center on Monday if you have any questions.